Fresh. This is Sati, and today I discuss about a very important topic, functional analysis. This is Banach space. Banach space. So let's start to study. And before we start this course, I must appeal to all of you subscribe this channel to get such kind of videos at first. Subscribe this channel. If you like, then like. And if you have any suggestion, then suggest me through comment. So let's start. First, subscribe this channel to get all these videos. So for Banach space, we first know about what is a linear space or vector space. Linear space or vector space. Linear space or vector space. It is very important to know to understand what is a Banach space. So a linear space or a Banach space is a linear space or a vector space is we need to take a abelian group with respect to addition abelian group abelian group we are taking L with respect to binary composition addition, and it has some properties, more properties to be a linear space. It has to satisfy through we can take if some scalars alpha, beta, gamma all are belonging to a field or a ring. So some authors also refer ring. I refer field. Field can be real or complex. It can be real or complex. So as the field will be, the scalars will be real or complex. The linear space will be called real linear space or complex linear space depending on the scalars taken. So here must it has to satisfy some scalar multiplication. This group, this abelian additive abelian has to satisfy some some one more property, scalar multiplication, scalar multiplication, 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 such that any I am taking beta belongs to this field and any vector x or y or z x, y, or z belonging to the this group G, sorry L, then beta Z must have to belong to the L, and it has to satisfy some more properties to be a linear space or vector space. First, that if we take gamma yz plus z, then this property with respect to scalar multiplication gamma y plus gamma z. Second axiom is that alpha plus gamma if we take y, then it should be alpha y plus gamma y. Third number is that beta gamma x vector will be equal to beta gamma x. And four is that one is the scalar identity, the multiplicative identity of this field. So 1 multiplied z equal to z. If this four axiom satisfied by any additive abelian group and with respect to scalar multiplication, all these scalar multiplicative vectors belong to this group, then we can say that this group generates linear space. Then we call that L respect to addition and scalar multiplication forms a linear space. I hope you have a very clear concept about linear space. Now we further know what is Banach space. Banach space very important in further analysis. To study further, you have a very clear concept of Banach space. So let's start. Uh, if we take a linear space, we'll consider a linear space. Linear space. I already defined linear what is a linear space. So we consider a linear space N on which on which a operation defined, which is called norm, on which the operation defined operation defined called norm is written in this way, and it has to satisfy some properties, and these are that any vector we are taking x, y, z, these are the vectors belonging to the linear space, vector space A, that norm of any vector, norm of y must be greater than equal to 0, and this norm will be 0. This norm of z will be 0 if only if z equal to 0. Otherwise, it cannot be 0. If norm represents a distance, like a modular mode, norm also like metric distance metric distance. It also norm also represents a distance. The second example is that it satisfies triangular inequality. This is called triangular inequality. Any two vectors y plus z, norm of y plus z must less than equal to norm of y plus norm of z. This is called triangular inequality. I'm not writing this. You have to remember this is triangular inequality of norm. So the third exam is that it has to satisfy this exam. This is the scalar defined on the field where the linear space is defined. All the scalars alpha, beta, gamma. This is the scalars defined in any field. This could be real or complex. This could be real or complex. So depending on the scalar, real or complex, we have to verify alpha x, it will be mod of alpha. If it is complex, then it does matter. That is, you have to take modulus. If it is a real scalar, then it does not matter. You have to take just modulus value, real, just positive value multiply norm of x. If these three conditions satisfied by by linear space, uh, where a operation called a norm is defined on the linear space, and the three axioms also satisfied by the linear space, then we will call that a non-linear space. Then n is called non-linear space. N is called non-linear space. Non-linear space or non-vector space. Now, how we will obtain Banach space? Here we have to do something. If this non-linear space is complete, if if n is a complete, here the complete is very important. Complete n is a complete uh, non-linear space. Non-linear space. Then n is called Banach space or n from Banach space. N is called Banach space. What does mean complete? Complete is a extra property uh, for which property we can call a space is a complete. So there, if we take series in this space, linear space N, all the series must be all the Cauchy sequence. If we collect Cauchy sequences from this space N, all the Cauchy sequences must be convergent. All the Cauchy sequences must be all the Cauchy sequences must be convergent. If this happens, then it will be complete. Otherwise, it cannot be complete. Must be convergent. So I am giving an example to clear to be clear about this. So uh, uh, our very well known uh, number system, real number system, or complex number system. Actually, if you will take any sequence, Cauchy sequence from this, these must be convergent from R or from C. All the sequences, Cauchy sequences are convergent. So, an R also form non-linear space, and complex numbers also form non-linear space. So, R and C are the most well-known examples of Banach space. We have to remember that R and C, complex numbers, set of complex numbers, are the well-known examples of Banach space. So, if R is a Banach space, then any dimension, if linear dimension Rn or Cn also are the Banach spaces. They are complete normal spaces. These are. So I hope you like this video. I will later also discuss many properties of Banach space and then start with Hilbert space. So keep watching and subscribe this channel. Thanks for watching.